Hi everyone, we are talking about audiophile cables. So, and we are just tackling the copper and silver cables. So it means just the material. So does the material selection make a difference? So I'm not going to review every brand and calling out specifically snake oil or not. That's not the scope today. Uh, this is just an educational video to so that you know and you are aware of what is the difference between plain copper, uh, OFC copper, and continuous cast copper, and silver, because there are physical differences between them and they behave different as conductors. And this is really basic stuff. This has been known for quite a while, and I'm just a little bit amazed at the general lack of knowledge in the audiophile community. And even when you look at cable manufacturers, they often neglect to mention this, and not because they don't know it. I think many of the cable manufacturers are well aware of it, but the simple fact that today everyone is so specialized that when you are in a field you take things for granted, and most scientists are really bad at explaining what they are working with to people who are not in their field. So now I'm going to give a helping hand for this. So the knowledge that circulates about wires and conductors is six elementary knowledge. So that's at the age, I mean not at the age, but at the level that people knew about conductors in the basically around the time that electricity has been described, almost like a very archaic sound, and what our young students and like my godson, who is about 10 years old, he at when he was 10 years old, he knew all of these things already. And most adults who are on the audio forums share that level of knowledge, and they have not progressed to learn about 20th century physics. And I'm not even going into 21st century physics, so let's just look at 20th century physics and step beyond six elementary education. So that common ground is that cables are looked at upon as conductors which have a certain resistance, and that's all that matters. And that's what the snake oil proponents cry, that that's all that matters for a cable, resistance. And if you want a better interconnect, better speaker wire, just double the gauge or make it shorter, or do both, and then you will have lower resistance, better current handling, and that will result in better sound. And they are halfway correct with this, and they are correct that if you do these things, so you increase the gauge and you decrease the size, then the resistance will go down and you will have bigger current handling. So your wire can conduct more before melting. And however, so if you take this principle alone, then for example, taking a gauge 6 aluminum cable, which is like a really thick aluminum wire, it should sound much better than a gauge 12 OFC copper or the finest silver. But when you compare, have you ever heard any audio cables that's made of aluminum? No, no one uses it. But think about that. If you are one of those snake oil people, just get a gauge 6 aluminum wire and use that instead of copper. It's even cheaper, and you don't have to worry about sound quality. However, we actually in the real world need to worry about it, and that's for two reasons. And now let's look at the first one. So people, when look at conductors, we can imagine it or as if it was a highway, and so the highway is your wire, and the cars moving in it are the electrons. And when the cars move in one direction, that's where the electrons go, and all of them are neatly ordered, go in the same direction, and they go at the same speed. And the speed is the voltage. So if there's higher voltage applied, then the electrons move faster. And if your wire has higher current handling capability, it's like having more lanes. So if you have a skinny gauge wire, then you have only one lane, and if you have a fat conductor, then it's like having a 4-lane highway, so it can propagate many more electrons. And that's how people imagine that wires behave, and the cable resistance is basically the speed limit. And if the speed limit is higher, then you can conduct more. And this is actually true only in case that when you have a superconductor. So if you have a superconductor, then this is how the electrons travel in your superconductor. That the electron flow is organized and they move at the same speed in the same direction. In any conductor that's not a superconductor, which means that in every single copper, silver, and aluminum wire ever made, the electrons move more like this. Not like cars on a highway, but like pedestrians on the walkway. And if you imagine, let's compare Trafalgar Square, and imagine that this is the direction either going that way or backwards. So you can go from left to right. That's the conductivity of your copper wire. Let's call this a longitudinal section of a copper wire. And you notice that the electrons, which is the pedestrians, they are not going all of them in one way. So this is where most of the electrons should be flowing. But like this person here is going that way, that person is going that way, this person is going that way as well. But look at that, there's a couple who is going the opposite direction, this guy goes opposite direction, this person is just standing there facing us, and look at that. There's a bunch of people here on the square, and they are not going anywhere. They are just standing there or moving from one corner of the square to here, and then coming there, going there all around, spend there like half an hour, half a day, and then they go to some random direction. And this is exactly how a real-world conductor behaves with alternating current. Because on the highway example, that was DC. DC means electrons go one way. And here, but DC, that's not music. Music signal is alternating current. So it means that the electrons go one way and then come back and then go the other way. And then go back and forth, back and forth, back and forth. So because of that, what you see is that most people who are going back and forth one way or the other are actually the people who are out here in the walkway, like in this area. So these people are going left or right. But those people who are in the center, let's mark it with gold. So the center in the square, they are not going anywhere. And this is how normal conductor behaves with alternating current, is that this is the skin effect. So the edge of your conductor, that's where the most of the conductivity happens. That's where the movement of the electrons is most organized. And at the center of the conductor, which would be the square itself, the organization of the electrons is very minimal. However, if this was DC current, it means that everyone is told to go from left to right. Then in that case, it would be an organized movement and there would be no skin effect. Skin effect appears because well, I'm not going into that. Let's just be aware that there is a vast difference between DC, that is one directional conductivity, and AC, which means directionality changes, and not just the directionality but the frequency as well. And you can the frequency is analogous to people walking. Some of the people walk very slow, that's like a low frequency. Some people are running, which is like high frequency, and some people run back and forth, and so on and so on. So basically what the resistance describes how your conductor behaves under DC conditions. So when only one way organized electron flow is happening. However, music is dynamic behavior, so electrons go back and forth. And now I'm going to show you the physics, actually how this looks like. Is that this is a cross section of a piece of silver wire. So this actually, I'm sorry, it's a longitudinal section, not a cross section. So this would be the cross section here, this line. So it means that this, let's say this is the left side of the wire, that's the right side, and this is the length of the wire. And it's a piece of silver wire, actually a piece of antique silver. It's less than it's like a hair thickness, really thin wire, and it's almost 3,000 years old. And as you can see in here in this area, there's a lot of damage that happened to it. But when we look with blue in this area, it's quite intact. So if you have a piece of silver wire in your gear, this is how it will probably look like 3,000 years from now. And how does it look like? So here you see the scale. So I'm just drawing it out here. So this much, that's 50 microns. So it means the 50,000th of a millimeter. And the crystals, the average length of the crystal pieces inside a silver wire is between 500 microns, so the 10 times of this, like that, and twice like that. So it's between this size. So, and when you look here, I will show it with red. Just check this out. So here, this thing, and it continues there. This is a single piece of silver crystal within the silver wire. So the metals, they are not continuous entities. So it's not like a strand of hair, but it's like tiny crystals pushed close to each other. And you see the differences between the crystal shards is that here this is a lighter color crystal, and here this is a darker color. It means that they show up under the microscope as if they were different colors, because they refract the light somewhat differently. And that's how you can tell that there's a crystal domain, there's another crystal domain. And the thing is that the metals conduct electricity extremely well within a single crystal domain. So for example, when we look here, then the electron starts traveling from there and goes to the end of that crystal domain. It has a clear path, and there's extremely low resistance when the electron flows within that domain. However, once that electron reaches the end of the domain, for example here, you see, but there's the end of that domain, and now it has to jump over to here, to that other crystal domain. And that's where the problem happens when you have AC signal. If you have DC signal, then you have just a slowing of the traffic. It's like the electron flow slows down a little bit before jumping to the next crystal domain, but the whole process averages out, and it shows up just as resistance for the wire. However, if you have an AC signal, then that's a problem, because if your electrons here spend some time before jumping to the next domain, by the time they decide to jump, the signal already changes, and your electrons are supposed to flow the other way around. So this jumpy thing, the jumpy travel of the electrons, creates a rectification effect. So all of these jumps between a single crystal domains rectify partially the electron flow, and that's why the AC signal is affected by the structure of the crystal. And then let's just now, I do not have an example of every wire type, but when we look at different wires, when we look at plain copper, the average crystal domain size is in the, let's see, can I draw that tiny? It's like this tiny, 10 micrometers. And when you have OFC copper, then it's 50 micrometers, like maybe like this. And when you have Ono continuous cast copper, then the domains can be up to 100 micrometer size. So it means that if you have an OFC copper, then a single electron has to jump 5 times less when it starts from one end of your cable and reaches the other end. 5 times less jumps, 5 times less rectification events, 5 times less smearing. And when we look at silver, even this tarnished 3,000-year-old, not even fine silver grade silver, then the average crystal domain length is 500 micrometer, but the crystals can be up to 1 millimeter long or even longer. So let's just look at, let's imagine that we are an electron and we are the passengers and we are traveling through a conductor. If you can imagine that as if you were a person who is traveling from one country to another and you are taking planes. When you are traveling, when you start, let's see, like this is one domain here, and this is the electron. So when you start here, it's like you are boarding the plane. And once you have boarded a plane that is a crystal domain, then your flight is straight and fast and without problems, with extremely low resistance. So you get there, and it's in life, if we were travelers, this is like arriving to the airport. So once you arrive to the airport, it takes a lot of time to go to disembark your plane, to catch your shuttle, go through to the other terminal, maybe wait for your baggage, and so on and so on, and then you catch your next domain and then travel there. So if you want to travel from one side of the world to the other, you can do it by catching 2 or 3 airplanes and you are there. But if you are an electron and want to travel 1 meter, which is the size of an average interconnect cable, then you have to make this much jumps. So if it's just a plain copper wire, you have to make an 100,000 jumps. So an electron changes conductors, basically changes boundaries within the wire. It's like going from one piece of wire to the next piece of wire 100,000 times. If it's OFC copper, then we are down to 20,000 times. Ono continuous cast copper, this is the one that they use in cartridges. So for example, Audio-Technica uses it in their mid to high level cartridges, but every cartridge manufacturer nowadays who builds decent mid to high class cables, they use Ono continuous cast copper wire. It only takes 10,000 jumps because this is the one that has the 100 micrometer crystal size, and silver just takes 2,000 jumps, which is 50 times less smearing and rectification effect than plain copper. So here, black and white, you see why silver is much superior as a conductor, because it interferes and slows down your signal 50 times less than a plain copper wire. And as you see, as the copper grades improve, the situation drastically improves. But even the best 6N continue monocast copper is still 5 times poorer or weaker than not even 3N silver. Actually, I put here 3N silver, but this is that antique 3000-year-old silver, and that was 99.7% purity, which is not yet 3N. It's below 3N, and that's 2000 jumps. The 3N soft anneal silver is much better. And when you look at that, there's another feature of metals called electron negativity, and which means that how much do they attract an electron which comes close to them, and for copper that's 1.90 on the Pauling scale, and for silver it's 1.93. So a tiny bit better, like 1.5% better than copper. So it means that in the case of silver, each jump requires less energy. So there's less signal lost per jump. So we have like 50 times less jumps, and with each jump we lose less. So that's why silver is truly a vastly superior metal for conducting AC signal, which music is AC. And that's why when you look at AC applications like radio, UHF, VHF frequencies, computers, they use silver-plated copper wire. And that's the reason for that, because silver behaves much better at AC, especially high-frequency AC, than copper. And that's why when you switch copper wire for silver wire, the biggest change is in the high frequencies. If you swap in a silver wire instead of copper, and you hear that the bass is much less, it's not because silver gives you less bass, it's because probably that silver wire's gauge was much thinner than the copper that you changed for. And if you go thinner gauge, then the mass current handling, and especially at the low frequencies, is not going to be anything near as what it was for your copper. But even if you have a much thinner gauge silver wire, at the high frequencies you are going to have a much more cleaner signal. And often that's not good, because it will reveal the problems with your amplifiers. And especially solid state amplifiers, they have a lot of weaknesses at the high frequencies, and copper, and especially plain copper, is just perfect for that, because these 100,000 jumps per meter mask these high frequency errors that the amplifier produces. And if you put in a nice silver cable or any kind of silver cable, then the masking is no more, and you really have to work on your amplifier. So that's a short message, that try out silver cable in your system, and if you hear that there are problems with the highs, it means that you have to fix your amp, your speakers, or something there, or maybe your source. The problem is never with the silver. The problem is in the gear. And if you try to fix the silver, then you will never ever solve your problem in your gear. So anyway, I think we just talked about all of these, that basically an electron flow in a wire is jumping from one domain to the next domain, and that makes a big difference. And now let's touch base of a very important issue, that metals are sensitive. So take care of your wire. So if you bend the wire, then these domains, these tiny bits of crystals, these shards, they break apart. So imagine that you have these nice long domains of crystals, and when you try to bend the wire, then these domains will fracture and break. If you bend your wire like in a really sharp angle, or like this, like a steep bend in any wire, will really destroy the crystal structure there. And if you just bend it at a very light angle, then these domains, they can slide along each other. There's a little play that can be given, and that's when these crystal domains will not suffer change. But and this is one reason why, if you are A/B testing cables, if you disconnect and connect a cable, you are going to bend your cable to a certain degree. And maybe when you A/B test, you will not hear the difference between those two cables, but you will also hear the difference between the damage you have caused in each cable. So if you have a heavier gauge cable, which is harder to bend, and you feel that you are trying to bend it, and you do not force it when you are changing cables, then you will introduce very few domain breakages. But if you have a super thin conductor and you change that interconnect, let's say a gauge 30 conductor, then you are going to introduce like millions of domain breakages, and that will really drastically impact sound quality. So that's why, guys, cable breaking and burning is a true thing, because what's happening is that as you start to apply current flow through your conductor, the damage made to the domains is repaired. So basically, when current flows, like electrons start to travel in one direction, then they will eventually melt these domains, and the domains will adapt over time and reform to be optimal for that current that you are using. So the crystal size of these individual domains will change, and unfortunately I have to add that for copper, if you apply very high currents to it, let's say you are really cranking your system and you like to listen at 11, then the amount of current, because there's so much rectification effect happening from a single crystalline domain to the other, and there's so many jumps happening, actually the copper domains break up and they become smaller and smaller every time. So you have your nice OFC copper or continuous cast copper, which have these nice big domains, and if you crank it really high, then they will start to break apart into smaller domains. And essentially you will end up after a while with many smaller domains. So this is what the reason for cable burnout. So that's why if you have like a 20-year-old interconnect, and it sounds really flat, like it doesn't have any top end, the reason for that is not because 20 years ago the technology sucked, but because there was fragmentation of the domains, and maybe that used to be an OFC copper 20 years ago, but by now the OFC has degraded into the 10 micron domain size plain copper. So, and going for silver, silver is a much more ductile material than copper, so when you bend copper, then these domains tend to break up and fracture, and silver allows a little bit of bending of these domains, and so because of that, silver is much more adaptable and longer lasting than copper. Aging is a really critical process for metals. So copper, when makes contact with air, it becomes copper oxide, which is non-conductive. So what happens to your copper wire, OFC or otherwise, as it ages, basically the edge becomes non-conductive, and this non-conductive region grows and grows and grows. So your conductive part of your copper wire becomes less and less and less. So over time, it will conduct less and less current, less and less electricity. And this copper oxide layer will also act as a rectifier barrier, and it will delay and reflect back high frequency signals into the current. So this is kind of like adding a reverse skin effect on top of a skin effect. So inside, when you have an AC signal flowing, then within at the center of your conductor there's very little happening. At the edge there's a lot happening, and when you go to the oxidized layer there's very little happening again. And however, both of these very little happening scenarios interfere with the main flow and will cause a signal smear, and that's why oxidized copper, old copper wire, when you see that it's green, that's when you have serious oxidation happening. You will not hear any top end, like the high frequencies are gone, and that's because of oxidation plus the domain breakage in the inside. With silver, the situation is quite different, because when silver oxidizes, it creates silver oxide, and guess what? Silver oxide is still a better conductor than copper. So even oxidized silver is better than copper. Just think about that. So when silver goes bad, it's still a step above the best continuous cast copper wire. However, there is a problem that can arise, is that silver can oxidize to another state, which is silver sulfide. And that happens when the silver contacts sulfur, and that can happen if you touch and contaminate the wire with sulfur from your hand. And the other thing, if you eat a lot of stuff that contains sulfur, such as you are boiling eggs. So if you boil eggs, there's like a ton of sulfides released into the air, and yes, it will eat up your silver wire. And this is the black tarnish on the silver, so that's how you can tell it. So if your silver wire turned black, it means it's silver sulfide. If your silver turns white, that's silver oxide. So basically, cable burnout is oxidation, and with copper you have only one choice, copper oxide, and that pretty much means the end of a road as a useful audio cable. But for silver, if it goes towards the oxide pathway, there is a very little change in the properties. If it goes to silver sulfide, then there is a noticeable change, and that's kind of like the silver magic going out of your system, and you have reverted back to plain copper. That's how oxidized silver sounds. And let's see, another advantage of silver wire over copper is that silver has the lowest contact resistance of any metals. So if you have RCA the best is silver. So if you have a silver male, silver female, contact them. That will provide you the best current flow. However, you will have to be careful of oxidation, and that's why people use rhodium plating and gold plating, because that's resistant to oxidation. But especially the rhodium plating, it's a really terrible conductor, and it really introduces a big rectification effect. And if you have like a couple of these rhodium blocks on your way, then it's going to make a really add up to a big degree. And another advantage of silver is that silver is extremely ductile, which means it's pliable, and you can even draw a 1 atom wide wire from silver. It's that soft, that's malleable. And when we look at at audio signal, just think about that you have to think about music, even in the form of electricity, when it's in your amplifier, when it's traveling through your interconnects and speaker wire, that it's a wave function. It's like this, like waves upon waves. And it's not a linear transfer, so the DC resistance will not tell you what the cable will do to your signal. It is a really complex flow. I'm going to show you a parallel to it. It's like, so if you want to see how electrons flow in a conductor, just imagine a river. So when you have a thick, heavy gauge conductor, it's like a biggish river, and all the water flows one direction, all your electrons going one way, and you see that the flow is very smooth. There are no waves. There's a tiny bit of choppiness on the surface where you see that if there's a wind, there's a breeze, you can see a little bit of shimmering. At the coast, there's probably a tiny whirlpools there, where there are stones and tree branches and roots. But at the grand scheme of plans, it doesn't make any difference whatsoever on how much water your river can flow. And that's true for audio cables as well. So when you are looking at really big signal levels at very low frequencies, let's say like a 20 hertz signal that will create a 20 hertz bass note, it's like your river that flows this way, and then there's a change in the tide, and then it flows the other way backwards. But it's a very slow, very gradual change. So there is nothing on the surface that you will notice about that change, only that you see that the amount of water is different in your cable. But what is at the bottom of your river, like there are rocks, tiny rocks, or maybe someone drove a truck and there's a truck in here somewhere, that doesn't mean anything at the end result. It's the same. Thousands of gallons of water will flow no matter what's at the bottom of your river. But when we go to a small signal level, which is like the micro details, microdynamics, then we get this scenario. Then anything that's at the bottom of the riverbed will make tremendous difference. And instead of seeing a flat surface, you will see these whirlpools and like a drastic change in behavior. And then you see like a sudden drop there where it accelerates, and then this part where the flow stagnates. So, and that's how the electrons behave too, when there's like a tiny amount of signal flowing, and so there's not much motive force for the electrons to jump from one domain to the next. And we also see high frequencies. So the higher the frequency, then the bigger these waterfalls will appear. So this is how you can imagine sound, and that's why metal quality matters when the signal level is very low. And all the fine details in music are buried in this very low signal level. And that's why if you have a very good hearing, then you can hear even the tiniest differences in conductor quality. And if you don't have any hearing, or maybe you work in a foundry, or you are into car stereo and you have blown your ears, then the only thing that you will notice is when you pump up the system and whether it can go to 11 or 15. And now just going back to what I mean, that just expanding on the wave transfer function nature of the music, is just imagine. Because there are plenty of naysayers who say that, oh, that's really tiny difference, just how tiny a crystal domain is, like 10 micrometers, I cannot even see that. Yeah, we cannot see that. But under a microscope, yes, you can. But how much difference does it make? Then let's look at violins. These two violins look almost the same, right? If you are an untrained person, you cannot tell any difference between the two. They have the exact same size, exact same number of strings, exact same shape. Everything is the same. They should sound the same. And in reality, they don't. Because here, this is a $200 beginner's violin, and this is a $1 million antique violin. And if the same person plays both of them, there's a night and day difference between. And that night and day difference is made by the tiny changes. So when you think about conductors, like the shape of the violin and the size of the violin, that's the gauge of your conductor. That's the gross quantity. That's the resistivity of your wire. But the fine structure, that's what makes the small differences in the sound. So both of these violins will produce the same SPL probably, or roughly, actually they won't, but they will be at the same order of magnitude, the same kind of sound, but the harmonic richness will be vastly different. And that's because each of the pieces, when you look at the bridge here and the bridge there, they look the same, but they are made from different materials, slightly different shape, different size, much more meticulously, so it will transmit the vibrations from the string to the violin's body with much greater efficiency. And that's like a tiny change. If they take out the bridge from these two instruments, put it in front of you, if you are not an expert, you won't be able to tell the difference between them. But a violin maker, a luthier, can instantly spot it and tell you that, okay, this is a 10-cent bridge and that's like a $2,000 bridge. And this is how that will sound and this will sound. And when you go through each part of the violin, all of that contributes to the overall character, and all of those contributions are relatively small. And that's how your system contributes to the sound. So when you go from your signal source, let's say your DAC, and you have an RCA connector, and then an interconnect, an RCA connector, preamp, RCA connector, interconnect, RCA connector, amp, blah, 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 blah. So all of these junctions are like the different parts of a violin. And when you add them up, they make all the difference. And these differences are really tiny. And the differences on the electron flow are also tiny. So if you have an ohm meter at home, you cannot measure these differences. Even with an oscilloscope is really hard. But if you have a real-time analyzer, then you can see these differences. If you have an electron microscope, you can see these differences. So these differences are real. These differences are in the micro domain, the micro scale, but in the music, the differences are also in the micro scale. So that's why cable quality matters. So thank you for holding on for so long, and live long and prosper, and please like and subscribe if you want to learn more in the future, and have a good evening everyone.